Hi there, welcome to Raelene Math. We're continuing on in our series on the Pythagorean Theorem by connecting the equation of a circle as an example of the distance between 2 points, which we saw was an example of the Pythagorean Theorem. Here we have a circle centered at point C with coordinates h, k, and we have a variable point on the circumference located at x, y. That point can change, so we use the variables x and y to indicate a changing location of point P. Now, anytime we have 2 points in the Cartesian plane, we can connect a line segment, and in this case, we can drop a horizontal and vertical line to form a right angle. This gives us a right triangle, which has 3 sides, A, B, and C, related by the Pythagorean theorem. So we know that we can start off using the Pythagorean theorem by squaring the base, squaring the altitude, and adding them, and getting the hypotenuse squared. But in this case, our altitude is given by a change in the y-coordinates. So I'm just going to label a point here. Let's call this R, which has the same x-coordinate as point P and the same y-coordinate as point C. I'm calling that R because this is really the radius distance. And then we know that A is the change in the y-coordinates from R to P, which is the bigger y-coordinate minus the smaller, y minus k. Similarly, our base is going to be found by a change in the x-coordinates to make a positive distance from the bigger minus the smaller x-coordinates. And so now when we substitute into the Pythagorean theorem, we have the base squared plus the altitude squared equal to the radius squared. And our base is x minus h, and our altitude is y minus k. Let's see this equation in action using graphing technology. Here we have the equation of a circle, but it's not immediately obvious that it looks like Pythagorean theorem. If we change the 9 to 3 squared, then we can see that we have base squared plus altitude squared equal to radius or hypotenuse squared. The center is located at 2, 1, and if we plot points 3 spaces to the right, left, up, and down of the center, then we can confirm that the radius is indeed 3 spaces. So from here we have the circle equation given by an extension of the Pythagorean theorem. Let's just rewrite the equation that we were dealing with. X minus 2 all squared plus y minus 1 all squared equal to 3 squared, or 9. And we can see the graph given by this picture, the center, and then 4 points indicated on the circle. Let's continue to build on this circle equation and the Pythagorean theorem by placing the center now at 0, 0 and considering a circle of radius r with a point on the circle called P. If we want to relate this to trigonometry, then we need to bring in the idea of the angle. And I like to measure the angle in standard position, and so I like to have the angle increasing from the base to the hypotenuse. Furthermore, we want to see a relationship between the sides of the triangle and the angle. And so in trigonometry, one such relationship is the ratio of the base, x, over the hypotenuse, r. And x over r is defined to be the cosine of the angle theta. Similarly, we can come up with a ratio for the height, or the altitude over the hypotenuse, as the y-coordinate over the radius, which is called the sine of theta. Applying the Pythagorean theorem says the base squared plus the altitude squared equals the hypotenuse squared. Taking the green equation and rearranging for x, we see that the base is equal to r cosine theta, and we can substitute that in here for the base and square. The altitude, if we rearrange this equation, gives us y is equal to r sine theta. I'll just put that in blue, and we can square that to substitute in for a. And the hypotenuse is the same as the radius of the circle, and so we get equal to r squared. Expanding this gives us r squared cosine squared theta plus r squared sine squared theta is equal to r squared. We can divide both sides of the equation by r squared, and we can simplify this equation to one of the most important trigonometric identities or equations. Cosine squared theta plus sine squared theta equal to 1. The word identity indicates that the left side is identical to the right side. So no matter what we substitute in for the angle theta, the left-hand expression will always equal 1. Let's take a look on a computer algebra system and do some numerical evaluation. If we substitute 0 degrees into that expression for theta, we get 1. And we can plug in a couple of different angles, 30 degrees, even if we substitute a negative angle like negative 41 degrees. We can substitute angles that are really, really big, like negative or 1,000 degrees, and so on. And so it turns out that no matter what we substitute in for the expression for theta, that expression is always identical to the value of 1. Another way to confirm this is to look at the graph of the function y equals cosine squared of an angle plus sine squared of an angle. And so here, when we plot this graph, we get a line. It looks like a line, and if we compare it to the graph y equal to 1, we can see that those two graphs superimpose. Especially if I turn off the blue, we see the purple graph underneath. So what we mean when we say that an equation is an identity is that no matter what we substitute in for the variable, the left-hand expression is identical to the right-hand expression. It makes a lot of sense, therefore, that this identity is known as a Pythagorean identity in trigonometry. Let's continue to build on this idea of a line segment starting at the origin and finishing somewhere at a point P in the xy plane. And we see that we have the idea of a vector when we have a directed line segment. And that vector can begin and end anywhere, but in standard position we can put the vector starting at the origin. What's really key here is that we have a right triangle once again, and therefore the three sides of that triangle are related by the Pythagorean theorem. In particular, the length of that vector, or the magnitude of that vector, is the same as the hypotenuse of the right triangle. So if we consider our circle over here of radius r, we can superimpose the vector, and now instead of calling it c for the hypotenuse, or the distance between 2 points, or the radius of a circle, we actually have v, which represents the magnitude of the vector v. And we have the horizontal component of the vector, vx, which is the base, and the vertical component of the vector vy. From here, we just relate by Pythagorean theorem once again. The base squared plus the altitude squared equals the hypotenuse squared gives us the relationship that the x component squared plus the y component squared is equal to the magnitude of the vector squared. And if we wanted to isolate for the magnitude, we would simply take the square root of both sides. So it seems that mathematics is playing a bit of a trick on us. Henri Poincaré says that mathematics is the art of giving the same name to different things. However, in this example, and other examples through the series, we've seen the opposite. Mathematics has given different names to the same thing. We represented two-dimensional distance by the Pythagorean theorem, relating the three sides, the altitude, the base, and the hypotenuse of a right triangle, as a squared plus b squared equal to c squared. Or, as I often like to put the base first, I'm going to write it b squared plus a squared equal to c squared. The reason I like the base first is because this represents my horizontal distance, which is related to x, which comes before y. Then we can also see that this is related to the distance between 2 points, and if we square both sides, we can rewrite it in this format. Another representation is as the equation of a circle. And we also saw that the fundamental trig identity, cos squared theta plus sine squared theta equal to 1, is related. If we multiply both sides of this equation by r squared, we can make this look a lot more like the radius and the hypotenuse are identical. Lastly, we saw how the magnitude of a vector is given by the Pythagorean theorem, especially if we square both sides. We see the same format in all of these equations. So I would recommend that you recognize Pythagorean theorem in its different applications, and instead of memorizing each case separately, understand the relationship and the connections between them. If you like this video, please click like and subscribe to my channel. Thanks for checking out Raelene Math.